Hello, and welcome to Physics for Play. In this episode, we're going to be looking at the mathematics behind superposing multiple harmonic oscillator motions on top of each other. Let's get started. Imagine you have a mass on a spring, and it's connected to another mass that's also on a spring, and that's connected to another mass that's also on a spring. And you've got lots of different masses connected by lots of different springs. You could describe the motion, which is now not going to be simple harmonic motion, but you could describe it as a more complicated motion where you superimpose the vibrations of all of those masses on all of those springs. So today we're going to be looking at how to deal with superposed motions. Now you might be thinking that, hey, wait, Santos, that's kind of a pretty specific made-up system. Very rarely do I, if ever, do I connect masses and springs together. So why am I ever going to need this? Well, to the extent that molecular bonds can be approximated by simple harmonic springs, or to the extent that any mechanical system and the joints in the mechanical system can be approximated with springs. This is a system that reoccurs in nature very, very many times. So it's something we really do need to pay attention to. And just to give you one example of that, we're going to look at diffraction patterns. So in this case, I am showing a double slit diffraction pattern that I pulled from the Wikipedia page for, I think it was for two slit diffraction. And you can see you get this nice colored light pattern. And this is from shining a laser through a diffraction grating, a two slit diffraction grating specifically. And in this instance, we happen to be talking about light waves, which is different from a simple harmonic oscillator, but there's a lot of common features. So you could imagine that this is the wall that the light is passing through. It's got two holes in it. You could imagine that there is a light wave coming from one source, a light wave coming from the second source, the second hole, and that those two light waves, each of which could be described as the electric fields at a particular point could be described as undergoing simple harmonic motion. And when we combine those two waves together, we get the sum of two motions. And this is something that happens all over the place. It happens for light waves, for sound waves. It happens for water waves. Any type of wave you can think of, this type of diffraction pattern is something that's going to be a common occurrence. So being able to superimpose these simple harmonic motions, whether it's for waves or actual mechanical oscillations like masses on springs, this is an important skill to have. So we are going to teach you how to superpose multiple motions, and we're going to be doing it by adding components of complex vectors. So to start off, let's review from our discussion about what happens when you're superimposing motion from complex vectors. So recall that we define I as the square root of -1, and that we define complex numbers as having both real and imaginary parts. So that if I write a complex number R, I have X, which is a entirely real number, which is the real component. Y is also a real number, but when I multiply by I, that second term becomes the imaginary part of that complex number. So imaginary or complex numbers have real and imaginary parts. And if we plot those, we take the real part and move it a certain number of spaces in the X direction. We take the imaginary part and of the complex number and move that number of spaces in the Y direction. And we can make a plot of the complex number in that way. So here is one of the complex plots we came up with before. Here, I'm just going to put 1 point in this. I'm just going to plot the point R. Oops. Let me do that. And now if I give it a more interesting point, you can see you're just going over 2 and up 3. And we talked about how we could represent that in different ways. So we talked about how we could represent, we could rotate that complex number in the complex plane by multiplying by I, or equivalently by multiplying by e to the I theta. Would give you a counterclockwise rotation by theta degrees. So we are going to show how to add simple harmonic oscillators, how to superimpose their motions by adding complex exponentials that look like e to the I omega t. I've taken the liberty of writing this code out already. So if you would like to, please go ahead and pause the video now, and you can copy this code into your workbook, into your notebook. And the two harmonic motions we're going to superpose are this one and this one. So it's going to be R1, which has an amplitude A1, which is equal to 2. And then it has the complex exponential e to the I omega t plus alpha 1, where omega 1 is the angular velocity, t is the time, and alpha 1 is the phase shift, which I am going to set equal to 0. Similarly, for the second harmonic motion that we're going to superpose, it's got an amplitude 2, an angular velocity of 1, and a phase shift of pi over 6, which is about 30 degrees. Not about, it is 30 degrees. And again, same functional form, amplitude times e to the I, angular frequency times time, plus the phase shift. And we're going to do a complex plot of that function. And we're going to plot a vector from 0 to R1, from R1 to R1 plus R2. So effectively, that's going to be a plot of the vector R2 starting at R1. And then we're going to show a vector that is from 0 to R1 plus R2, so the combined vector. Just go ahead and run this. And actually, let me change one thing here. Just want it to run a little bit slower. So what you can see, we have R1 in orange, R2 in that yellowy green color, and the sum of the two vectors, R1 plus R2, in that blue color. You can see that I add vectors as you did in intro physics just by connecting them head to tail. So R1 plus R2 is the resultant vector R1 plus R2. Now, these vectors were all functions of time. And the simple harmonic motion that gets described is what you get when you project these vectors onto the real axis. So right now, R1 has a length of 2, whereas R2, the yellow-green, has a length that's a little bit less than 2, because you can see it starts at 2 and ends a little bit before 4. These vectors are functions of time, and they will rotate in the complex plane as functions of time. And you can see that rotation here. So you could imagine projecting a line down from the blue line, and that would be your superposed motion. As you can see, it's undergoing circular motion in the complex plane, which means that when projected onto the real axis, it will be undergoing simple harmonic motion, which you can see if I just plot it out. So here we're going to plot just the real component, and we're going to plot that. Let's go to 10 pi, we put in a plot theme and some frame labels and some label styles to make the plot look nice. You can pause the video and copy that. But as you probably could have guessed from above, this plot will just give simple harmonic motion because the blue vector is really just moving around in a circle, and we know that's simple harmonic motion. I can change things about this. So I could change, for example, the amplitude of the second motion. So when I do that, that'll change the length of R2 in my diagram. You can see R2 is now half as big, which effectively means I have a shorter R1 plus R2, but other than that, it hasn't really changed all that much. It's still undergoing simple harmonic motion or circular motion rather, which when we project it onto the real axis is again just going to give simple harmonic motion. Things get a little bit more interesting if I start to change the frequency at which these are oscillating. So let's say I were to double the angular frequency. So now this harmonic motion is happening faster than this harmonic motion, which you can see because the harmonic motion for any individual vector is just how quickly it's rotating around in the complex plane. And now you'll see that since R2 has a faster angular frequency, it's going to rotate around twice as fast as the complex vector R1. And you can see the green vector is doing exactly that. What does that do to the superposition of the two vectors? Well, you can see that the superposition vector in blue, the R1 plus R2, well, now all of a sudden that's not just moving in circular motion. Circular motion involves moving at a constant radius, and the radius of the blue vector is changing. It's going in and out as it goes around the circle. So this will mean that we will not have simple harmonic motion. If we were to plot that out, let's check and confirm that that is in fact the case. And you can see that's definitely not a sine curve. It is periodic, but it is not a sine curve. So when we are superposing two simple harmonic oscillators, and they do not have the same frequency, you will not get a sinusoidal curve. You'll get something that might be periodic, but it's not going to be simple harmonic motion. It's not going to be just sinusoidal. Let's tweak this even further. So let's see what happens if I don't just use frequencies that are integers. Let's see what happens if I plug in an irrational number. I'm going to plug in the square root of 2 here. We'll show the motion quickly. And it'll be difficult to tell what's going on here just from this limited animation. But you'll be able to see it a bit better in the plot here. So notice what we had this time. It's not a sine function, but it is very periodic. I get the same shape in the curve every time. When I rerun this, plugging in an irrational number for the frequency, all of a sudden it doesn't even look periodic anymore. In fact, even if I extend it over a larger period, there's no more periodic pattern here. To get a periodic pattern, I'll let you work out the math to prove this on your own. But you need omega 1 and omega 2. They can differ. They can be multiplied by integer values relative to some standard frequency. But if you start putting irrational, if the ratio of these two is not a rational number, if it's an irrational number, then if the ratio of the two frequencies is an irrational number, you will not get periodic motion anymore. There is another way to examine this motion and another plot that you can make. Because here we've been adding vectors in the complex plane. Here we've been plotting what the resultant vector, the summation, the superposition of those two vectors on top of each other is like. We can also make what is known as a Lissajous pattern. I hope I'm pronouncing that correctly. But that's what you get when you superpose the motion of the two vectors, but you do it perpendicular to each other. So in this case, we're looking at plotting R1 on the x-axis and R2 on the y-axis. But really what I mean is plotting the real component of R1 on the x-axis and the real component of R2 on the y-axis. And we're going to do this with a parametric plot taking t from 0 to 100. Actually, to start off, let's again go simpler here. So we'll start with frequencies that are the same, and we'll start with both of these identical. So they're in phase, same amplitude. Everything's the same. So R1 is equivalent to R2. You can see that'll just give me a line that's moving in circular motion. It'll give me just a sinusoidal motion for the superposed motion. And in this case, since R1 equals R2, you can see that R1 just equals R2. It's just going to be y equals x. It's going to look like a plot of y equals x. We can, again, make this a little bit more complicated by putting in some relative phase. So I'm going to put in a phase of 30 degrees, pi over 6. You can see now my R1 and R2 are out of phase in the complex plot. Nothing too much is going to change in the plot of the superposed motion. It will change the amplitude since now the blue vector is not quite as long, and it'll shift the phase somewhat. But for the most part, it's still simple harmonic. But the Lissajous pattern, when you are out of phase, you start to see this ellipsoidal pattern. And if you go 90 degrees out of phase, so pi over 2, you can see that's now 90 degrees out of phase. If we compute the Lissajous pattern, now we have a circle. So when you're in phase, you're getting a straight line for the Lissajous pattern. And when you're 90 degrees out of phase, you get a circle. What happens if you're 180 degrees out of phase? That's easy enough to test. And you can go through and look at all of these. So 180 degrees out of phase. It looks like there's something going on here. It's really not. There's just some round off error here, which is why this number is ridiculously small. But this is really just round off error. There's no actual motion here. It should just be a flat line, which if I change the scale from -1 to 1, you'll see it just looks like a flat line. Again, it's just the noise pattern you saw there is just some round off error. What would the Lissajous pattern look like for motion that's 180 degrees out of phase? So that means when R1 is 1, R2 is -1, so you just have a negative sloping line. What about if we start changing start moving at different frequencies? So let's say one is moving at twice the frequency of the other. We have seen this before. You can see what shape that blue curve is tracing out. You can, let me get rid of my plot range since I don't need it anymore. You can see, again, we have periodic motion, but it's more complicated. And the Lissajous pattern starts making this, looks like a parabolic shape. And if I shift the phase ever so slightly, that changes the shape there, and then that broke the symmetry a little bit, and you can see the symmetry is broken there as well. still kind of a nice, simple, interesting pattern. We can, I can increase the frequency a larger amount. You can see that you get an even more complex pattern. Let's show that a little bit more close up. And for my Lissajous figure, you can see it gets more complicated. What happens if I go back to that aperiodic pattern? Remember, when I put in an irrational number, like the square root of 2, my motion was no longer periodic. What will that do to the Lissajous pattern? Well, the Lissajous pattern closes on itself, which is why I get these patterns that are finite. But if I have something that is not going to be periodic, there's no way it can close on itself. So you can see you start getting very complex patterns that fill in the whole space. So these are some neat tools for exploring superposed motion. You've got your Lissajous patterns. We can just plot what the superposed motion looks like. We can graph it in the complex plane. What if you want to superpose many motions? Well, I'm not going to spend the time to actually write out a whole bunch of harmonic oscillator equations in the complex exponential notation. I'll let you do that on your own, but I will show you what happens if we define a pattern here. So let's say we have a bunch of harmonic oscillator equations, and they're, in principle, each one can get a different amplitude, a different angular frequency, and a different phase shift. All I'm going to do, so in principle, all of these can have different functions depending on which harmonic oscillator we're talking about. But we're going to, what I'm going to do is I'm going to define each of them to have the same amplitude, the same angular frequency, but I'm going to shift the phase by pi over 4 radians and see what that gets us. So I've defined, so n here is the oscillator number. So for the first oscillator, n is 1. For the second oscillator, it's 2, all the way down to however many oscillators I want. And we are going to, again, plot the motion as a function of time, or animate it as a function of time. We're going to do it with a complex list plot. I will let you copy down the code for this. All I'm really doing is exactly what I did up here for this plot, except I'm doing it for n complex numbers that we're adding together now, n harmonic motions. So I'm going to define, I'm going to just say n equals 10. And we'll put in the 10 motions here. And you can see when I add these together, here's my first vector, here's my second, here's my third, fourth, fifth, sixth, seventh, eighth. The ninth one overlaps with the first one. So you can see, I probably need to actually give this a plot range. The reason I need to give it a plot range is just that the scale is going to resize if I don't, and then we're not going to be able to easily see what's going on. We'll try that. That's too small. Well, we'll try that and see. So you can see how adding your vectors, what adding your vectors looks like. Let me do a smaller number here so it's easier to see. So all we're doing, again, connecting the vectors end to end. The resultant vector is just the one from the beginning to the last point. I won't draw it in here. I'll let you figure out how to do that on your own. But once I have this, I can start combining frequencies and amplitudes of all different sorts. So I could, let's say I make the frequency go up by n every time we do this. And ooh, I'm sorry, I messed this up. This should have been a delayed equals, a colon equals here. Let me reevaluate this. So now each of these harmonic vectors that harmonic motion vectors that I've added will have a different frequency, and that will make the motion kind of a mess. But the superposed motion, again, is just going to be that last. It's just going to be the sum of all these vectors connected here and then projected onto the real axis. So if you project this last data point down onto the real axis, that tells you what the motion will look like. And you can, as you can probably gather, this is going to be a pretty bizarre plot that we're going to see. It's not going to be a simple harmonic motion sinusoidal oscillator. We can see that by looking at a plot of the motion. So to get a plot of that, I am just going to copy this. We'll go all the way up to n. And we'll go ahead and plot that. Actually, let us be lazy because we can. Do that. Take this. This is what we want to plot. And as before, if I try to plot this, I'm going to get nothing because I want the real part of it. And you can see we start to get interesting patterns there. And I'll just make sure we get the right label. This is the resultant vector. Vector, not vector. Let's make that a little nicer. Yeah. So if let's see if I can, well, I'm going to stop there. I will let you play around. You can see what happens as you, if you use more complicated functions for how the superposed motions are changing. You can get some interesting shapes and some interesting superposed oscillations just by playing around and tweaking some parameters. But the video is getting a little long, so we're gonna stop here. We will see you next time, where we will be talking about normal mode analysis. Go ahead and like the video if you liked it, and if you'd like to see more of these, please click subscribe.